Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to a new discussion which is Surface Hydrologic Modeling, and this is part 1. Of course, the input is going to be the digital elevation model. So, this is also a derivative of digital elevation model, but through this surface hydrologic modeling we can create several derivatives. So, input is of course digital elevation model, but this modeling concept comes from surface hydrologic modeling, and again several derivatives we will have, starting from like watershed boundary, drainage network, and sediment transport and density, yield, and wetness index, many such parameters which we can derive from surface hydrologic modeling. So, we will discuss in 2 parts. So, let us start. Now, as you know that whenever we say word model, here 2 models, one is the digital elevation model and then surface hydrologic modeling. So, model is basically here the surface hydrologic modeling, that to model the flow of water across a surface, and surface here is digital elevation model. So, we are using one model to model the water flow over the surface, and specifically I have used this term over the surface. So, this is important, which will come later in the discussion why I mentioned over the surface. Now, as we know that the shape and characteristics of the earth surface is useful in many fields of study, especially like in civil engineering, in earth sciences, in hydrology, in geography also, and nowadays in environmental studies also. So, this shape and characteristics of the surface and what is which model or what is the data which can represent the characteristics, that is the digital elevation model. And this understanding about the surface characteristics will also allow us to see how changes in composition of an area are taking place or will take place in future, and how water, when it flows over the surface, how it creates different features or boundaries, like watershed boundary, another thing, which is of course a topographic boundary as well. But water flow or this plays a very important role. Drainage network is also developed because of water flow on the surface. So, we can try, and what we will have through this surface hydrologic modeling using digital elevation model to answer certain questions like what happens when deforestation occurs. So, the forest creates a impediments in the flow of water over a surface. So, if plantation is removed or forest is removed, what would happen to that thing? You recall the very first discussion on GIS or in this course, I showed one watershed through 2 different pictures, and there I showed that if in one area the forest is removed, deforestation takes place, then what is going to happen to the soil moisture condition in that particular watershed. And in the second scenario, it was that if at another place the same equivalent area of forest is removed, then that scenario will change. So, different conditions will bring different results, and many such things can be simulated, modeled, predicted before anything really happens on the ground. So, your GIS, your digital elevation model and surface hydrologic modeling all will allow us to predict and see or visualize what would happen if any action is taken on the ground. Now, how does this affect the watershed? I have given the example. If forest deforestation occurs, it affects the soil moisture condition. And if soil moisture condition is changed, it will bring changes in soil erosion. It will bring changes in groundwater conditions and many other things. So, any change on the ground, on the surface of the earth which takes place in terms of vegetation or drainage or change in elevation, all will bring changes in some way or another. Maybe immediately or maybe after some time. It depends what action is being done on the ground. And also we can answer through this surface hydrologic modeling that how can these effects be mitigated? How we can minimize the impact, if at all the development, because development should not be stopped. It has to take place. And at the same time we have to take care about the environment and surface of the land. So, how best we can bring a scenario where minimum damage occurs to the environment. So, that can also be modeled through GIS and surface hydrologic modeling. And therefore, this combination of digital elevation model and surface hydrologic modeling in GIS has brought many applications, which we will see even how these will affect the groundwater conditions, or how we can think or visualize the groundwater conditions or changes in groundwater conditions can also be there. So, not only in civil engineering, in hydrology, in earth sciences, but in various domains these applications are there. Now, before we really go for this surface hydrologic modeling, we have to understand how water flows on the surface and how it develops a drainage system, because this surface runoff is not uniform throughout the surface of the earth. So, it basically develops the drainage system or river network or stream network. So, basically what it means that the area upon which water falls, basically this includes all kind of forms of water. So, in total we say precipitation, and when we say rainfall, it means only water in form of liquid. So, whatever the precipitation which occurs on the surface of the earth, ultimately it will go through or move through the network, which is our drainage network, and through which it travels to an outlet, that is a watershed outlet or basin outlet, and entire system, entire this thing where it happens is called the drainage system. So, flow of water through a drainage system is only a subset of what is commonly referred as in a part of hydrologic cycle, because hydrologic cycle is big. Even the water which is going in through evapotranspiration and then it goes in the atmosphere, it condenses, rain occurs or precipitation occurs, and then again it flows. So, hydrologic cycle is very big. But there is a contribution of drainage system to hydrologic cycle, and this whatever is the part of hydrologic cycle, which also includes, as I mentioned, precipitation, evapotranspiration, and also groundwater flow. Surface hydrologic modeling also basically focuses on the movement of water across a surface or over the land, how water will flow, how this surface runoff will occur. Now, further in order to develop our basic understanding before we go for real surface hydrologic modeling, we have to also understand a drainage basin or drainage system is an area that drains water and other substances to a common outlet. Now, other substances might be your sediments, very common other substance, maybe pollutants, or maybe other like wood and other materials. So, all these are carried through this drainage system by the water. Here some terminology which we will be using. So, those who are not familiar about this, for them it is fresh, but those who are know it is a refreshing for them. That the important point here is this outlet of the watershed, and this topographic height, which is creating a watershed or boundary topographic boundary is called basically watershed or drainage divides. It also calls drainage divide. Why drainage divide? Because whatever the drainage network which we are seeing is all contributing to this outlet. And the interesting part is that one watershed ends, another watershed starts over the land. So, over the entire globe, there is a continuous, this is continuous. The size and shape of watershed may change. That adjacent watershed may have a completely different shape and size, but one watershed ends, another starts, and all over the land of the earth this is true. Now, watershed, but same time we also use some other words like basin and catchment. All are contributory areas. Basically what they are doing, they are whatever the precipitation occurs in this drainage divide or topographic high area, and which is divided by the or which is depicted through this watershed boundaries, will all fall, whatever the precipitation will occur in within this boundary has to come out from this pour point or outlet. There may be some loss of water into the atmosphere through the processes of evapotranspiration, or there may be some loss of water into subsurface through groundwater. So, if we include those, exclude then whatever is surface runoff which will occur, which has to come out from this outlet. Now, within a watershed we can also have sub watersheds, like here it is shown in a light green color. So, each drainage line or stream can have its own watershed. For example, I can also, if I do not have currently the topographic map or drainage this digital elevation model in the background, but if I decide that this is my outlet, then this can be my watershed like this, and if I decide that this is the outlet, then this can be my watershed. So, as you go lower and lower towards the outlet, the watershed or sub watershed becomes larger and larger, and as I go higher and higher in the order of stream. So, this we say first order stream, we will have full discussion on this. So, if I decide my outlet is here, this watershed is going to be only this much. So, within a watershed we can have many sub watersheds. Now, other common terms for drainage area, I have just mentioned that watershed, basin, catchment or contributory area. Whenever we use word watershed or catchment, catchment is used in other domain also and can bring some confusion also. But when we say watershed, it is the really related with hydrology. And whenever we say watershed, it means we are not talking of a very large area. And when we say basin, we are talking about a very large area. For example, we will say Ganga basin, we will not say Ganga watershed or Ganga catchment. So, there is some difference, but there is no quantity attached to this, that if a watershed is more than 100 square kilometer, it would be called basin. There is no such classification. So, generally for a smaller size, relatively smaller size, we use word either watershed or catchment, and when it is very large area and this watershed, then it becomes basin or contributory area also. And in a canal system, we will call them as a distributory area or command area, which is just opposite to the watershed or basin. So, this area, that is the watershed area, is commonly or normally defined as the total area flowing to a given outlet or pour point. Now, pour point, I have just explained, that is the point at which water flows out of the watershed. So, it may go out of one watershed, but may enter in the larger watershed or a larger basin, and till it reaches to the sea. And this water outlet is generally or usually the lowest point along the boundary of the drainage basin. It has to be the lowest, so that whatever the precipitation is occurring will come out through this outlet. and the boundary between two basins or watershed is defined as a drainage divide or watershed boundary. So, if this is the boundary and if rainfall occurs here, then it has to, and surface runoff occurs, it will come out from here. But if rainfall occurs there, then there will be another watershed and the outlet might be in this direction. So, that will come out like this. So, this becomes the outlet for that. So, basically it is also the precipitation which falls in whatever in the boundary will come out through surface runoff other. Now these drainage network or stream network which we see in form of these, generally they are represented in maps in blue lines or black lines. This network, drainage network through which water travels to the outlet, can be visualized as a tree with the base of the tree is at the outlet, as you have also seen here. Like here what you see, that this is my base of tree and these are the branches which are other lower order streams. Now the branches of the tree are the stream channels, and the intersection of two stream channels is referred as a node or junction. So in GIS. So here this may be one stream, same first order stream, and this is also first order. Now when two first order streams meets in one scheme, they become second order, and likewise we keep adding. So that means the intersection of two stream channels is referred as a node or a junction, or for downstream it may become a other order. And sections of a stream channel connecting two successive junctions or junctions at and the outlet are referred as the stream links. These stream links are very important while deciding the order of the streams. So through surface hydrologic modeling, that derivative can also come, that whether streams are following, there are two well known, well established methods, whether stream method or stream method, which we will discuss later. Now as I have been saying, it is a topographic divide. Watershed boundary is also a topographic divide. So if you see a map which is a topographic map, and wherever you are having higher points or contours are having like this or spot heights are also there, then that becomes the watershed boundary. So using a topo sheet and with some care, we can definitely draw a watershed boundary quite easily. But if we are having GIS and digital elevation model, we can do all these things very accurately and automatically through this surface hydrologic modeling. So traditional watershed delineation, which we have been doing earlier when we did not have the GIS and digital elevation model like today, by using contours on a topographic map. And a watershed boundary can also be as sketch, how you start doing or drawing on a topo sheet, that first you decide which is going to be your outlet, like in this case, and then you start searching a boundary, or that is through your contour lines or a ridge, and by which then you complete the entire watershed boundary and you come back to the same outlet. Now let us discuss a surface hydrologic modeling. So far we have developed some basic background about some terms which we will be using here. Now this first and the only input basically is required initially is the digital elevation model. Interesting thing is here is that surface hydrologic modeling is more or less sequential. So in that way it is very simple to understand. And second and most important thing in surface hydrologic modeling is that we are having one assumption, a belief. Assumption is here, which is a very big assumption. The assumption is that whatever the precipitation will occur, it has to come out through the outlet. And that means we are assuming there is no loss of precipitation or no loss of rainwater, neither to the atmosphere through this evapotranspiration, or neither to the ground nor to the groundwater. So, whatever the water, even a single drop, if it falls on the in a watershed, it has to come out of out of your outlet or out of your watershed. This is the only assumption in surface hydrologic modeling. So, input is digital elevation model. The first thing which we do generally is we drive the flow direction. Flow direction is more or less like your slope map. Then we identify the sinks. Why sinks? Because this is what I just mentioned about the assumption. The sinks are the depression, artifacts, error within your digital elevation model. So, again a 3 by 3 kernel will be used, and if any cell is found that there is water will not flow out of that cell, then it is labeled using the surrounding 8 cells values, and it is labeled. That means the sink is filled, and that means the water then will flow. Otherwise, there will be stagnation of water in that lowest cell out of 8 surrounding cells. So, sink identification has to be done. I will show you some images also, or DEM with sinks. And then once you have identified the sink, you are already having one output which is flow direction. Now you have to fill these sinks, no problem. There are algorithms, there are the software is there, and very easily you can fill the sinks. So now you are having a digital elevation model which is devoid of sinks or depressions, which you have already identified and filled them. Now your digital elevation model after this sink fill becomes a depressionless DEM or sink proof digital elevation model. Now this will go for further processing, and the next step to calculate flow direction, flow accumulation, sorry. Once flow accumulation has been calculated, what exactly flow accumulation is, what is flow direction, we will be discussing subsequently within this lecture or in next one. Now, using this flow accumulation, one can drive stream order using 2 well established methods. You can drive stream to feature, that means the drainage network in vector form, in polyline form, and also you can drive stream link, which are again very useful from for flow modeling point of view. Further, using this depressionless digital elevation model, you can calculate flow length. You can also get a snap pour point. That means manually wherever you will click, a watershed boundary can be delineated. And then finally, you can for your input digital elevation model, just giving the threshold value, you can delineate watershed whichever the present in your digital elevation model. The only problem which you will face in the boundary areas, because as I have said in the early discussion, that one watershed ends, another starts. So, when you are having a boundary or margin of a digital elevation model, there you do not get the watershed in the adjacent. So, only that part will have a limitation, not really error but limitation. Otherwise, for within that digital elevation model, you can drive watersheds of your desired size, that would be decided based on the threshold value, and that is basically the area which you give. So, it is basically this surface hydrologic modeling, as you must have realized by now, is a sequential modeling, means step by step you can do it quite easily. Now, as you know that the most common input is going to be a digital elevation model, and we have already developed the understanding, and this data is used as input to quantify the characteristics of the land surface and how water will flow, and that can be modeled through surface hydrologic modeling. Now, here the accuracy part will play a very important role. If your input digital elevation model is good, good means quality wise, accuracy wise, then obviously you would have a better results. This is true in all the cases. Now, other factors which will affect our accuracy are like whether your input digital elevation model, because it is a grid. So, you can have a cell value as integer or floating point. Floating point, since it is having high precision, and therefore, the accuracy of your output is going to be very high. But if you are having input points, input of digital elevation model and cell values are integer, that means generally these are in meters. So, you will have the least count is 1 meter, and therefore, the accuracy will affect. So, this depends. If I am creating my own digital elevation model, then I should keep the cell value as floating point or real numbers. Now, there is one type of error which can be rectified by first identifying sinks or peaks or depression and then filling them. So, part of the problem is already solved, and the rest will depend basically the spatial resolution part. And a sink, as I have already explained, that sink an area surrounded by higher elevation values, and basically 3 by 3 kernel is used to find out the pit or a sink's depression, and the center cell is analyzed. If 8 surrounding cells are having higher value than the center cell, then center cell is identified as a sink, and later on you fill it. Because if it is not done, then it will develop its own internal drainage, and then whatever the precipitation which is occurring will not come out, will not flow on surface as a surface runoff, and neither it will come out through the outlet. In many cases, generally it will happen that whatever the precipitation is occurring will form a surface runoff, and ultimately it will come out. But there are many natural conditions which may not happen like this. If it is a heavily forested watershed, there will be completely lot of delay. It depends on the what type of rocks are present, what type of structures, geological structures are present, and what type of soils are present, what type of vegetation is present, any human activities, and some other like whether it is a glaciated or not, or a snow covered or not, whether it is a karst area means terrain of limestone terrain. So, all these, because limestone terrain is generally having internal drainage. So, on surface you do not see the drainage, but internal drainage. So, there the surface hydrologic modeling may not predict as you wish to have, because it will not follow that assumption. The assumption is that even a single drop of water, if it falls on the surface in a watershed, it has to come out through the outlet. So, in many conditions this assumption is not fulfilled, but nonetheless in many conditions it is full. Even if it is not being fulfilled, still we can exploit and see how it affects the groundwater, which we will discuss little later. Similarly, when we identify sinks, we also identify peaks, but peaks will not affect much in that way. But nonetheless, in that process everything is identified, then it is made sure that whatever the water which is dropping on the surface in a watershed has to come out of outlet. Now, this flow direction, that is, these are the more commonly natural features, and the area less determined to calculation of the flow direction. And errors are such as of these like sinks or peaks should be removed before attending a device to derive a surface information, or before we go for next step in surface hydrologic modeling. Because water has to flow, that is the assumption. If it is just in one cell, becomes stagnated, then it becomes a problem. So, sinks may be areas of internal drainage like I have said in case of limestone terrain, or can prevent a downslope flow routing of water. Now, here is the example. There may be a single cell may be representing a sink or a depression having a multiple cells. In this example, there are 5 cells which are having depression. So, all surrounding cells here are higher value, having higher values than these pink colored cells. So, we identify them as a sink, and the rest as you can see, the contour lines are also shown here. These are not watershed boundary, mind it, this is contour line, and stream network also shown here. So, basically cell containing the contour line are assigned the value of the contour. All other cells are interpolated in a manner that no sink will be there. So, sinks are always possible in areas where contours coverage near a stream. Now, sink or areas of internal drainage is a cell or set of cells which are spatially connected cells and whose flow direction cannot be assigned. So, for flow for that purpose also we have to do that part. So, generally in practice what we do, that once we take the digital elevation model, first we do this sink identification and filling, then we go for flow direction and flow accumulation and other derivatives. That is always, because if there is error, let us remove at the very first stage. Now, the number of sinks in a given digital elevation model is normally higher for coarser resolution DEM. So, in a relatively if you are having a coarse resolution digital elevation model, the area which will be covered by these sinks is going to be very high, and in a high spatial resolution digital elevation model, it is the just reverse case. So, in this case, for surface hydrologic modeling, if choice is there, it is always better to go for relatively high spatial resolution digital elevation model. But as when we have been discussing the quality of a digital elevation model, we also discussed that high spatial resolution does not always mean a high accurate digital elevation model. So, that one has to also remember. Another common cause of sinks in a digital elevation model results from storing the elevation data as an integer number, not as a real number, and this can be more troublesome in areas of low vertical relief. That means the area which do not have much undulations, and you may have problem. Now, it is not uncommon to find 1% of cells in a 30 meter spatial resolution DEM to be sinks, but 1% is nothing in that sense. Now, this percentage can increase by multifolds if we are having a 90 meter, the 3 arc second equal to 90 meter roughly, and 1 arc second equal to 30 meter. So, 3 arc second digital elevation model. Now, I am having an example on the same digital elevation model which we have been using throughout this course. So, this is the DEM, and when DEM is subjected for identification of sinks, you can see these red dots, these are sinks have been identified. Some are single cells, some are having set of cells. So, identified sinks here is total number is 186, whereas digital elevation model total number of cells are 99 times more than this roughly. Now, once we have filled the sinks, then we come to the next step, and that is your flow accumulation, or before that flow direction. So, these tools, hydrologic modeling tools or hydrologic analysis tools, basically have been designed to model the convergence of flow across a natural drainage system or terrain. And the assumption which I have already mentioned is that the surface contains sufficient vertical relief that a flow path can be determined, that whatever is falling in form of precipitation has to flow, and it will create own path through a drainage network in form of drainage network. And these software tools operate on the assumption that any single cell water can flow in from many adjacent cells, but out through only one cell. Now, when we go for the delineation of water sets using surface hydrologic modeling or defining a stream network be processed through a series of steps. That is why I said earlier that surface hydrologic modeling is a sequential modeling. So, series of steps one by one we will go. Some steps are required while others are optional depending on the characteristics of the input data and whether we really require those outputs or not. And flow across a surface will always be in the steepest downslope direction. So, whichever the cell is having more difference in terms of elevation, there the water will flow from the center cell, when if we think in terms of that 3 by 3 kernel. Once the direction of flow is decided out of each cell in the known, it is possible to determine which and how many cells flow into any given cell. So, each cell has to flow out, but in how many cells will flow out in one cell, that will be also determined through flow direction. And the information then can be used to define watershed boundaries and stream network. So, these are two derivatives through the surface hydrologic modeling, very popular one, or you can say first order derivatives. So, the flow chart which we have discussed, again I am going to show which shows the process of extracting hydrologic information such as watershed boundaries, stream network, it is through using a digital elevation model. Whatever the purpose of using this surface hydrologic modeling, the start point has to be always as a digital elevation model and identification of sinks and filling of the sinks. So, elevation model or digital DEMs are used to determine which cells flow into other cells, that is flow direction. This is the flow direction which I am talking. Now, if there are errors in the elevation model, which we have also touched upon this issue, then like maybe a limestone terrain, a karst topography or karst geology, there may be some cells locations that are lower than the surrounding cells and internal flow might be there. So, there is a limitation of surface hydrologic modeling. That means, in those conditions the surface hydrologic modeling will fail, because the assumption here that each and single drop of water has to flow as a surface runoff and has to come out of a watershed. And if in case of karst topography or the all water travelling onto the cell will not travel out, and if that does not travel out, then this surface hydrologic modeling will not work. So, this our tools, the surface hydrologic modeling tools which are available in most of the popular GIS softwares, will allow to identify sinks and give you tools to fill them. I have shown the example also. And ultimately then you will have a depressionless elevation for further processing. Now, one of the outputs or derivatives of surface hydrologic modeling using a digital elevation model is delineating a watershed. That is, the first pour point needs to be identified for that. And usually these locations, the pour points, outlets, are the mouths of the stream or other hydrologic points of interest such as gauging stations. So, when in the beginning of this discussion, when we have been discussing about this part, and the terms which we are going to use about watershed, there we have already discussed this part. And in this surface hydrologic modeling, once the pour point has been identified, then the system will automatically delineate the watershed. Of course, the stream network and other things will also be done. And this watershed, this creates the watershed once you have selected a pour point for each stream segment. That means sub watershed, you can go to a single stream between the stream junctions. And to create the stream network, the first flow accumulation for each cell location is calculated. So, this is virtually the fourth step. The first step is to identification of sinks, filling of sinks, flow direction, now flow accumulation. Now, in case of flow direction, how it will look in terms of digital values. So, here we are having a digital input digital elevation model. Here we are having this 3 by 3 kernel and a coding system. So, for each direction we are having code 1. This is, though it is a number, but it is a code. That means we will not do any arithmetic operations over these codes. For the southeast direction the code is 2, for south direction code is 4, and for southwest direction 8, and likewise. So, when this 3 by 3 kernel moves all along over a digital elevation model, this is how it will have a flow direction. So, 128 means it is flowing in the northeast direction. Now, let us see for these cells that here this is 58 and this is 61 and 68. So, 68 is very high among these. So, this will flow in this direction, that is in the northeast direction. Similarly, we can understand the other. So, flow direction, while calculating we use this concept of 3 by 3 kernel using codes. So, flow direction, a conclusively definite line or course in which something is issuing or moving into a stream. Now, on the left side you are seeing a flow direction derivative through surface hydrology modeling, and on the right side you are seeing flow accumulation. Though here you may feel that only few lines in form of drainage are visible, rest is not there, but each cell is having a value which you can check while zoom it and using identification tool. So, that is why I said earlier also that the flow direction is more or less like an aspect map, very close to that concept, but the coding part is little different, because these numbers are required, not the northeast southwest, these numbers are required in different calculations. So, that is why the coding system has been adopted for flow direction. Now, stream network can be delineated using flow accumulation theme, this is which is the fourth derivative, and flow accumulation is its simplest form. We can say that the number of upslope cells that flow into each cell, because drainage network will be decided, stream network will be decided based on the number of upslope cells. And by applying a threshold value, that if 100 cells or 1000 cells are flowing at a outlet, that becomes my pour point, and then watershed boundary or drainage network can be delineated. So, by applying a threshold value in terms of number of cells to the flow accumulation output or theme, a stream network or a watershed boundaries can be calculated. And for example, to create a raster where the value of 1 represents a stream network on the background of no data, and the tool parameters could be as follows, that for example, threshold value equal to or more than 100 cells. So, that can be this is what it has been done. Once it is applied, drainage network, now flow accumulation, you are seeing lot of drainage there, and using that I can identify these drainage. So, from raster I can convert into the vector. So, the blue lines which you are seeing, and in the background you are seeing a shaded relief model, which is again derivative digital elevation model. These blue lines are vector drainage network, which has been derived through the same DEM through this surface hydrologic modeling, where the threshold value was kept at 100. Now, once the stream is created, a stream network is created, it can further be analyzed for stream order and stream links, which are again useful in some other modelings. So, stream ordering, sweep methods and stellar methods, two methods are well established. In first method, when the two links intersect, their magnitudes are added and assigned to the downslopes link, like here. So, order 1, first order, when these two adds up, it becomes the second order. When second order and first order becomes, again it goes for the this is the sweep, the first method. So, first order, it becomes second order, first order and second order it becomes third order. This is the sweep method, the first one. And the second one is the stellar method, where the first order of course becomes second order, but second order and first order will remain second order. And when two second order streams meets, then it becomes third order, not the fourth order, as in case of here. So there is only little difference, but the stream order is very simple and this is most popular. However, in good standard GIS softwares, both stream schemes, ordering schemes have been implemented. So whichever you like most, you can use them. Now stream ordering, as you can see, there are other methods also. Apart from the stellar and stream, there are methods. Horton has worked a lot on in this, because you have also seen the new algorithms for slopes, aspect and other things. Hack method, and of course a topological method that is based on the topology. So in literature you may find 5 stream ordering schemes are known. However, as I have mentioned, that in softwares only either stellar or stream or both have been implemented, not many. Personally, my choice is for this stream method, which I find is very simple. After all, we have to give some order. So let us take the very simple example. Now stream ordering has been done. The drainage network which I showed, which had the background of shaded relief model, here stream ordering has been done. You can check using the stellar method, and for the same drainage network it has been done for a stream. So this is, say for example, this is first order, and then there is also a small one. So it becomes the second order, and then second order, first order becomes the third order and one more order becomes the fourth order, and likewise you go. So in this example only you are having 4 orders. So this is one like watershed boundary, which we will discuss later. Stream ordering, stream network can be derived. So these are the few outputs which we get through surface hydrologic modeling. Further outputs and further discussion we will have in the next part. With this I end. Thank you very much.